it's a great place for showering. When they break up the tough walk.
Good morning, everyone. Happy New Year, and welcome to our first forum for 2016 of the Wolverine Caucus, which is generously brought to us by the UN Alumni Association, as well as the Office of the Vice President for Government Relations. I'm Dr. Veronica Wilkerson-Johnson, and I am delighted that all of you are here today to join us for a very important and very timely topic on sustainability. We have a renowned speaker here to talk to us today, and he wants to be very interactive with you. And so we're excited that he's here, and I'm going to have Senator David Knesset from District 5, the great city of Dearborn Heights, where I'm from, to introduce our speaker. I also want to welcome Representative Marcia Hovey-Wright and any others who have joined us, and Rebecca DeBoot, State Relations Director from the University of Michigan. So without further ado, Senator David Knesset.
Well, good morning, everyone. Oh, my Lord, let's do that again. Good morning, everyone. Good morning. All right, thank you. Again, my name is David Knesset. I have the great privilege of serving in the Michigan State Senate, representing the communities Dearborn Heights, Garden City, Inkster, Redford Township, and Detroit. To be forthright with you, given all that's going on in Lansing today, it really is a nice reprieve to be with you all this morning and to be able to introduce what I know is going to be a phenomenal speaker, an individual who brings so many professional accomplishments to the table to share with each and every one of you. Really is a privilege for me to be able to introduce him this morning. Brought my notes so that I wouldn't make any mistake, and so I hope you can bear with me as I introduce our speaker today, Dr. Greg Keolian, who is the distinguished Peter M. Wege Endowed Professor of Sustainable Systems at the University of Michigan. He teaches interdisciplinary graduate courses on sustainable energy systems and on industrial technology. He earned his PhD in chemical engineering from the University of Michigan in 1987, when I was a healthy 1 year old. He also teaches at the University of Michigan School of Natural Resources and Environment and in the Department of Civil and Environmental Engineering. Dr. Keolian is also the director of the Center for Sustainable Systems at the University of Michigan, celebrating his 25th year. His research focuses on the development and application of life cycle models and sustainability guidelines to broadly improve our society's products and our technology. He has led over 50 life cycle projects of diverse systems, including analysis of conventional and alternative vehicle technology, renewable energy technologies, building and infrastructure, consumer products and packaging, and a variety of food systems. Over the past 2.5 decades, Dr. Keolian has collaborated with a wide range of businesses across diverse sectors, national labs, and government agencies at the national, state, and local level. And so I hope you'll join me this morning in welcoming today's guest speaker, Dr. Greg Keolian.
Thank you, David. I appreciate it. Good morning, everybody.
Good morning.
Thank you, Veronica. Thank you, David. Appreciate the warm introduction. It's a pleasure to be here. I'm Go Blue all the way from undergrad. Got my doctorate at Michigan too, and now I'm a professor. So it's a pleasure to be with this group and talking about, I think, a very important topic. We're going to be focusing on energy, which is really the lifeblood of our economy, and looking at the future. And we have a diverse audience here. We have legislators, staffers, and we have a bunch of us as consumers, right? So I'm going to try to cover this topic from different lenses so that you come away from here, hopefully, with some new knowledge that might help you direct a more sustainable energy future for our state and for our nation. So I'm going to be talking about energy both in terms of supply, the issues there, and then also looking at energy demand. And I do work on life cycle modeling, so I look at how products are made, how they're used, how they're retired, to develop a profile of the environmental performance, sustainability performance of those products and technologies, and look at ways to improve them. And I'm going to share with you some perspectives on different systems. So we're going to look at transportation, we're going to look at buildings, and if we have time, maybe we'll get to food. And that could be interesting. And if you do have clarifying questions along the way, just please raise your hand. I'll try to make this informal, interactive. And so let's get started. So first, a definition of sustainability. This comes from the Brundtland Commission. That's Gro Brundtland there. She's former Prime Minister of Norway, former executive director of the World Health Organization. And this commission came up with this definition, which I think is very profound. It's development that meets the needs of the present without compromising the ability of future generations to meet their needs. So it's really the actions we take today. We want to ensure that there are resources, adequate resources for future generations. There's environmental quality for future generations. We don't want to compromise that. So sustainability is really looking long term. Okay? But it's actions that we take today that have effects long term. I mean, it could be actions related to infrastructure, which can be long term. It could be energy infrastructure, it could be water infrastructure. It's important that we take this perspective. I work on specific tools, life cycle assessment, life cycle cost analysis. So we look at energy, we look at cost, but it's a way to measure performance of sustainability. So I'll introduce that to you as well. But just to begin, in terms of challenges for Michigan, in terms of our supply, we are relying heavily on non-renewable resources. So by definition, that's not sustainable if it's non-renewable. They have a high carbon intensity, so there's a lot of greenhouse gas emissions associated with the use. In terms of our demand, in terms of challenges, I think the building sector is one where we have a lot of old stock, particularly in urban areas, that's inefficient. Okay? And then sustainability has environmental, social, and economic dimensions. So one is about affordability, energy insecurity, particularly for low-income households. So we'll talk about these, and just a little bit of background to get us started. In the United States, if you want to know how much of our energy system is renewable, you can see here 10%. So here's our petroleum, our nuclear, natural gas, coal. So we really need to shift this. If we're looking long term, once you use petroleum, it's burned up, it's no longer available. We've depleted the stock, the endowment for future generations. So we really want to be expanding this. If we take it down to Michigan, and this is all energy, both used for electricity, but other means such as transportation fuels. We look at Michigan, we're about 7%. Okay? And one of the big drivers that's moved us to increase our renewable content has been the RPS. And I'll talk about that, the Renewable Portfolio Standard. But we don't have a new one to drive improvement into the future. And this is kind of benchmark us with other states a little bit. We put in place an RPS, and actually our center did analysis of the cost in terms of, or basically the economic impacts in terms of jobs and in terms of overall cost of the RPS, and then what kind of improvements in terms of reducing emissions from that. And was pleased that the state did adopt a 10% RPS, so that 10% of our electricity is from renewable sources by 2015. So that's really driven improvement. But you could see other states, have higher, like Minnesota, 26%, and actually 31% by 2020. So this is really actually been key to transforming the grid in the United States, to changing the fuel mix, this policy, a very profound one. And, we had a moderately aggressive one in place, which is good. Now, we burn fossil fuels. Those fossil fuels have a greenhouse effect. And just recently, the convention in Paris established some pledges to reduce our carbon emissions. This is a trajectory of carbon emissions. And if we want to avoid adverse effects of climate change, we need to go to one of these paths that really reduce those carbon emissions. The green path would be nice. That's very aggressive. The pledges kind of put us on this orange or red path. But even with that, those pledges by all the nations, we're expected to exceed 2.5 degrees increase in temperature, which has a big impact in terms of the environment. Scientists actually want us to get down below 2 degrees C. And again, this is really about the future, okay? The gray-haired people like me, it's probably not going to have an impact. It's about our kids and grandkids where we need to take action on this. So the United States has actually pledged to reduce some 28% by 2030. In terms of Michigan, we did a greenhouse gas inventory for the state of Michigan. It was published in 2005 and worked on some strategy. One of the strategies that was implemented was RPS, but again, we haven't gone beyond the 2015 target of 10%. But now what's going to become important is this Clean Power Plan, which I know is being discussed in the legislature here. It's an EPA rule to reduce those carbon emissions. Okay, it calls for our state to reduce by almost 40% by 2030. And our Center for Sustainable Systems, my colleague, did a study to look at a least cost plan for Michigan. And it involves efficiency improvements as well as an increase in renewables, equivalent to or corresponds to approximately 28% renewable by 2030. Okay, so that is going to, again, drive us towards more renewable energy if we adopt this particular approach. So we are moving in the right direction, hopefully on supply, but it's really critical, and we're talking about sustainable energy, again, that we focus on shifting our supply. I'm going to be talking to you about different products and systems today, and it's important when we're looking at energy that we recognize that a lot of the decisions we make, a lot of the policies we're putting in place have long-term effects because these products have long lives. Okay, cars could be 10 years old, 15 years old. You get a furnace that could be 40 years old in your house. You look at buildings like the University of Michigan. I'm in a building that's over 100 years old. So we're making decisions that will have effects in terms of energy demand and consumption over long periods of time. So we want to implement technologies that have and systems that have high efficiency. It's really critical that we do that because changing over these systems takes time. It's a slow process. So it's very important when you make purchasing decisions about refrigerators, about vehicles, that we pick technologies that are most efficient if we want to really look at sustainability. So I want to introduce this life cycle modeling to you, give you a little crash course on what I do, what I've been doing for 25 years. Okay? So I look at how products are made. So I start out with raw materials and how those raw materials like iron are turned into steel, and then how the steel goes into a stamping plant and produces body parts for vehicles, and they're assembled. We use products. We then retire products, and hopefully we can remanufacture, reuse products. We might have to service them before we retire them. And to come up with a profile of the product, we draw a boundary around the system and we look at all the inputs, the materials and energy going into the system, and then all the outputs in terms of water pollutants, in terms of air emissions, solid waste, and we develop a profile. And we could see where the impacts are along the life cycle and target those for improvement. So we did one of the first comprehensive studies of mid-size vehicle, working with Ford, GM, and Chrysler at the time in these material industries to establish a baseline. And so if you look at an automobile, and this took 3 years to model this, 20,000 parts and components. This is the result after 3 years. It shows you the energy for producing materials, for manufacturing, and here's use. So use really dominates. The use of your automobile really dominates the life cycle energy. And this is, you can see there are 1,000 gigajoules and 6 gigajoules is the barrel. But if I look at this, I could see, well, how could I reduce the energy? Well, one way is to lightweight the vehicle, right? If I lightweight the vehicle with aluminum, this is going to go down. But aluminum is very energy intensive. So the material production can go up. And that's why this framework is very valuable. You can look at the trade-offs that occur, and ultimately what you want to do is reduce the total impact. So that's what we do. And we've done a lot of lightweighting work, but I'm going to show you some of our analysis of electrified vehicles. This is an important strategy to improve sustainability, is vehicle electrification. How many of you have a hybrid vehicle? Anybody have a all-electric vehicle? Plug-in electric vehicle? Good, we got one plug-in. All right. Well, we did some analysis of the volt. And what I'm showing you here is the total life cycle greenhouse gas emissions for this volt. And on this axis here is the amount of driving in electric mode. So 0 means you're driving all gas. 1 means you're driving all electric. And these lines here represent where you're charging your vehicle in the United States. Okay? So in many cases, as you drive more in electric mode and charge with electricity, your life cycle greenhouse gas emissions go down. Okay? Question?
Question. And I've never seen a comparison on electric vehicles versus gas-powered vehicles in terms of what energy was used to create that electricity. Do you deal with that?
That's exactly what I have here. Perfect question. Perfect question. So what we have here is showing you these colors correspond to what regions in the country you're charging your vehicle. So if you're up here in the New England states, you actually really reduce as you go more electric because they have a lot of hydropower. Okay? These lines up here, you actually increase your greenhouse gas emissions if you're charging in these states because they burn a lot of coal. Wyoming, Montana, Colorado, your emissions are actually going up. Okay? We're in this grid here, so our emissions are somewhat going down. But what this points out is that if we really want to take advantage of electric vehicles to enhance sustainability, we need to shift our grids. We need to shift exactly what you said, the fuel mix, to make them less carbon intensive, right? So that's a really key point. And we actually did this project through support from the Department of Energy working with China, and we're looking at the China grid. And here's China. They burn a lot of coal. So they have a strategy for electrification, but they're actually, as they go more electric, they're increasing carbon emissions. So it's vital that they change their grid as well. So we need to shift, and shifting takes place through changes in behavior, through regulations. I'm going to step back and introduce this concept of the iPad equation to really look at some of the drivers that impact, let's say, gasoline use or carbon emissions for vehicles. And this equation was actually formulated by a physicist and an ecologist, and Holdren actually is the chief scientist that advises the president, John Holdren. He's a physicist, came up with this equation which says that impact is driven by people. It's driven by, they use the term A for affluence, which really represents consumption per capita. And then the T term represents the environmental impact per unit of consumption. So it's a little fuzzy concept. I'm going to try to make it clear, more clear. I'm going to look at impact of automobiles in the United States in terms of the gasoline used. So that's shown here in 1970 and in 2009. We increased 66%. Now, what was driving that increase? Well, our population grew 50%, right, from 200 to 300 million. Our driving, which is the amount of driving vehicle miles traveled per person, went from 5,000 to almost 9,000. Okay, 70% increase. So you drive more, you burn more gasoline. Now, how much gasoline you burn depends on your fuel economy, and this is the average, so it's gallons per mile to calculate this. So it's the inverse of the fuel economy on road, and in 1970 it was 13 miles per gallon. We improved to 20 miles per gallon on road average. So this went down 36%. So technology here did make some difference, but unfortunately it's not enough to offset our increases in population and our increase in driving over that period. So we're consuming more gas. So this is a pretty powerful equation, and so this is going to drive our new fuel economy standard is going to reduce this T term. And it turns out we're starting to saturate with the amount of driving, right? There's only so much driving you want to do in a day. And we're starting to saturate. So we are going to make progress here. But this is really coming through these new regulations on fuel economy. For many years, so I went from 1970, which was here, to 2009, there was some improvement, but we were pretty flat. And actually, our state had a lot to do with keeping this flat. I hate to say it. Our leadership wanted to keep this flat. But now we're on this trajectory, which should help with regard to transportation. All right? And now we were talking about the automobile, but I want to broaden the topic of transportation, and we'll look at different modes. So I'm going to ask you a question. Which of these do you think is the most efficient mode of transportation? Railroad, okay. Any other? Airplane? You could include, I don't have the statistics on that, but walking is going to be pretty good, and biking. All right, well, let's just see the result. This is the energy intensity for these different modes in energy BTUs per passenger mile. So this is how much energy to move us, one person, 1 mile. And it's kind of surprising, the result. So you see the transit bus actually is consuming the most energy. This is a U.S. average. Planes are actually more efficient than the cars. Okay? Here's our rail. And so the big factor here are these numbers in parentheses. And that's where there's real opportunities. Now, the planes are pretty efficient because, on average, there's 100 people on each plane. So you ride on a plane these days, you're pretty packed in, right? We don't particularly like that, but as far as efficiency, that's good. But if you take, I use a bus periodically in Ann Arbor. Sometimes I'm the only one on the bus. That's not a good thing, right? So we really need to do a better job utilizing vehicles. And if you look at cars, on average, it's 1.6. And I think commuting to work, the average occupancy is around 1.1. And you can't go below 1, right? Unless you consider people being on their cell phone and not paying attention to driving, then it's less than 1, right? So there's opportunities to improve in terms of mobility with better utilization of vehicles and modes. Yes?
This is talking about passenger travel, but it isn't freight travel is much bigger concern? I mean, uses more energy.
In the United States, actually, passenger is bigger than freight, but freight is also important. And in terms of efficiency for freight, moving it by train is very efficient compared to truck. In addition, if we could move it by sea, by ship, that's even better. But obviously, you're limited in terms of moving it within the United States. So the other thing, we've done a lot of work, and I don't have time to really go into this, but we've done a lot of work looking at sustainable infrastructure and looking at our roads. So we've done a lot of life cycle modeling of roads, asphalt versus concrete, and engineered cementitious composites, a new material, and basically looking at over a 40-year period, how do you optimize with respect to energy, with respect to cost, and looking at these different events, reconstruction, maintenance. And in this, we've taken into account the cost of the materials, the construction, but we've also taken into account fuel costs, so you're driving, and that's important because when we have a reconstruction event, we disrupt traffic flow, okay? So we waste more fuel. We also, as the roads get older, we waste fuel because the surface isn't as smooth. We take into account the value of your time sitting and waiting there because of a construction event. There's damage to vehicles. So we take this kind of life cycle perspective, and I think it's very valuable. And it turns out that with regard to the schedules that MDOT set in place for rehabilitating roads, our analysis showed that it was optimal with respect to life cycle costs. So if you follow what they want to do, it would be optimal in terms of dollars. Now, unfortunately, they haven't been able to follow the recommended schedules for maintenance because they don't have a budget to do it. Okay, but that's a whole nother topic, I guess. But we've done some work on this. And so there's a bunch of things here that I kind of outlined with regard to mobility and energy that I think are important. The use dominates. There's efficient modes that are underutilized. Electrification is a good strategy, but we really need to take advantage of that. We need to shift to more renewable energy. This framework of life cycle could be very valuable when we're looking at things like road infrastructure. Now, there's a challenge today in that the OEMs in Michigan are trying to encourage efficient vehicles, electrified vehicles. But when you have inexpensive fuels, it's difficult to sell, right? Efficient vehicles. So that is a challenge. I think fuel is inexpensive. I enjoy cheap fuel, but I think there's a real opportunity to take advantage of that low fuel and have a revenue that could deal with things like roads and help with low carbon policies. That's my perspective, but all right. So, yes.
Bit of speculation. The younger generations are, we boomers, we moved out to the suburbs. Now the younger generations are moving back into the cities.
Right.
I saw recently an article, I was surprised that a surprising percentage of them don't even have driver's licenses. Mm-hmm. Is this something you're watching? Is this
yes, and
mitigate?
This will reduce the VMT, and many are living closer to where they work or living in urban areas. So that's going to help. That's definitely going to help.
It's too early.
Yeah, this statistic. No, part of we're seeing this reduction in VMT, and part of that is, and we are. That's evident. It's a good point. All right, I want to turn to question.
Just really quick, do you have autonomous vehicles in your equation for how we use the road?
We're doing research on autonomous vehicles, and I think the real opportunities with autonomous vehicles are for shared autonomous vehicles in a community as opposed to a privately owned autonomous vehicle that you're going to send out to pick up a pizza and bring home. We could actually increase VMT with autonomous vehicles. So it's very important, but we're doing research on looking at opportunities to enhance sustainability with autonomous vehicles. Where does it make sense? So I want to turn now to residential homes, and this is a house in Ann Arbor that we modeled, and we basically took that house and redesigned it and putting in efficient systems in terms of insulation, in terms of lighting, in terms of windows. And so we were able to, and we had to evaluate all the materials going into it. How much do you think this house weighs in tons? Any idea? 15? Anybody else? 40? It's about 300 tons of materials that go into it. An efficient house, a little bit more. But in terms of the energy, we cut the energy use down by 60-some% with this existing technology and cut the carbon emissions accordingly. Yes?
What would the payback period on the investment?
It's a good question. I got some numbers for you coming up. But first, looking at the energy, this is the standard house. This is the energy in terms of construction, in terms of materials. This is the use. So like the car, the use phase really dominates in terms of energy use. The efficient house actually uses a little bit more to construct, but you could see dramatically reduces the use phase. And you could go to a zero energy house, which it's not zero because you have to build the materials. That's the trend that we could see. Now let's look at the cost. When we did this study, we actually worked with the builder. The price of the house was $240,000. We did the analysis of the cost of the efficient home. It was $262,000. It was our estimate. Builder says, I'm not going to build it. Nobody's going to want to buy it. They're not going to want to pay $20,000 more for the house. This was some years back. That was kind of before the market of people being interested in green and efficient homes. Well, let's look at the cost. Here's the mortgage, $546,000, maintenance, and then these utilities, $40,000 and $32,000. Efficient home, more of a mortgage, but we dramatically reduced the electricity and natural gas. If we look at the total life cycle, it was about the same. But my hypothesis is that if you do what's right from an energy sustainability point of view, it's going to make sense economically. Because one thing that generally happens, although we're not seeing it in the short term, is energy prices go up. So this was in 1998. I put in 2012 prices. Now you see the efficient home is actually less in terms of cost than the standard home, right? So these are decisions we make. Do you pay the $20,000 more and have efficiency over the life of the house, or not? And so it's decisions about capital versus operating, right? And we tend to emphasize the initial cost, right? The capital cost over the life cycle cost. But the big takeaway I want out of this is for you to really think about life cycle costs. Not just think about the immediate cost, but think about life cycle costs. And it's particularly important if you look at low-income households, right? Low-income households, it's very difficult to buy a new home. So they buy a used house, and they're stuck with this, right? The other important thing here is when you look at the efficiency of homes, there's minimum standards that are set. So there's residential energy codes, all right? And our state has adopted, and this was difficult to achieve, a 2009 international code in terms of efficiency. And I remember we did the analysis of policy for the state in terms of carbon reduction. We were proposing that they adopt this code. And that was difficult because the homeowners association and the state didn't want that code adopted because that could raise the price of homes, and they see that as less sales. But again, you got to look life cycle. Anyway, this got adopted, but I want to, again, this is a kind of a benchmark. Here's where we are. There's a 2012 code and a 2015 code. So these states are actually 2015. In Michigan, we're 2009. All right? And this determines the efficiency of that house going forward. So any comments about codes in Michigan? Yes?
So when you make that analysis, do you assume the house has a finite life then?
Yes, that analysis was based on 50 years of life. Okay, any advocates for the 2015 code for Michigan? How many want to support that? That's easy to raise your hands, right? All right. I mentioned affordability as an issue or security. So I have a colleague that's doing work on actually energy justice and pointed out that there's a couple of programs to help with dealing with affordability and energy. One is a weatherization assistance program, which leads to lower operating costs, lower life cycle costs. So this is basically to help homeowners put in place insulation to reduce the cost in terms of heating and cooling. The other program is low-income home energy assistance, and this is where government money is used to pay the utilities for low-income households. So it basically pays the bill. This is where the money has gone. So it's been mainly for assistance in terms of paying bills. But it's not changing the condition of the house, right? The more efficient thing to do is to weatherize, to reduce the cost, and allow the family to pay their own bills, right? But we tend to emphasize a strategy of just paying the bills, not changing the efficiency. So does this make more sense to you, weatherization over? Yes?
What do you think about that Carnegie Mellon study about the weatherization? I don't know.
I haven't seen the Carnegie Mellon, but is it about the effectiveness of the weatherization?
Yeah, basically saying it wasn't cost efficient to do.
Well, so when you put insulation on houses, it definitely reduces your heating bill. I mean, I did that and I saw dramatic reductions. Now, you could look at efficiency, and there's a lot of different strategies you could take in terms of windows, in terms of insulation. So it depends on what you're doing, right? Yes?
These days, if you look at the forward curve on gas futures, you can go out 10 years and hardly see anything much above $4 or $5 a thousand feet, which is maybe half what it used to be. Are your economic assumptions really incorporating that kind of a view of future heating costs?
Well, when we did the life cycle model of that house in Ann Arbor, we had different scenarios in terms of prices. So we did look at different scenarios in terms of escalating, declining, and all of those are important. Okay? But what is really important, when we're talking about sustainability, it's not about just reducing energy, it's also about dealing with climate change, which I tend to really emphasize as a big issue. Because, 50 years from now or 40 years from now, there's going to be some significant effects in terms of our climate, in terms of sea level rise, which can lead to flooding, and in terms of the coasts, and these are big effects. And I know it's difficult to look out to the future, but when you put all those things together, I think it makes sense to put in place insulation and to reduce costs.
I'm just saying that the economic assumptions that underpin a lot, and I was in the area, have been radically changed.
Yeah. No, I agree with you. Yeah, you have to go back in terms of the calculus, and it would probably shift back to the 1998 numbers, but I don't think we're going to see for 40 years that natural gas price, you know? But, you know, there's uncertainty. Yes?
One of the problems with weatherization assistance is that people don't want to help landlords pay to improve their houses. And a lot of the low-income people who need help are renters, not owners.
Right,
That's
right.
a big part of the problem is you
Right.
can't, it's difficult to sell to the population helping
Right.
people who own houses and rent them out to give them money.
Right.
to improve
No,
their
I agree with you. And so those are definitely challenges.
When you get back to the business of your grandchildren and their grandchildren and stuff like that, that longer piece, doesn't that change the whole discussion even more? In terms of, for example, if there is no oil left, that is meaning that you're going to have to deal with, or no coal left, all that sort of stuff. I know that's maybe way too.
No, that's why we have to emphasize that. That's why we need to shift to things like renewables, because frankly, we want to be able to use natural gas to make things like plastics and chemicals. So if you burn those up, that feedstock is gone. So you're exactly right. I'm just going to give you one more trend here on buildings. Our houses have gotten bigger. And interestingly, over that period, the occupancy has gone down. So this is not a, thank you very much. So I talked about the use phase dominating. Some of our patterns are not sustainable. There's a large existing stock that's inefficient that we have to focus on. You know, we need incentive programs. The codes, I think, are really critical. And then, you know, I think that weatherization is more important than throwing money in terms of assistance. I wasn't sure we're going to get there, but I was going to quickly do food. But
Well, I does want to comment that in Moline, Illinois, where John Deere is, they've got this huge pavilion downtown with all their agricultural equipment on display.
Right.
And they actually have a prototype of an autonomous tractor.
mm-hmm.
Farmers sit there in the living room with the screen. It's pretty cool. And my question was going to be, have you looked at the amount of energy and usage and how much energy is it taking to produce our food?
Yep, that's where we're going.
Where you're going.
So I'm going to get, so we have done life cycle analysis of food systems for many years now, where we developed the first sustainability assessment of the U.S. food system. And I'm not going to give you all of we had some 50 metrics that we evaluated, but I don't have time to go through the 50. This is today focusing on energy. So this is the amount of energy that goes into our food system for production, processing, packaging, transport, retail, commercial, your storage, your refrigerators. This is 10 quads of energy. The U.S. uses 100 quads, so 10% of our energy is going into our food system, and this is what we get out. So this is the calories that are available, and it turns out calories available, there's 3,900 calories per person per day that's available. Now 30% of it is wasted food, we don't eat it, and then some of us overeat, including me, eating more calories than I should. So I just pointed out the household, this one right here, your refrigerators. So we did some analysis about when you should retire your refrigerators, and we looked over this time period and looked at if you wanted to minimize energy, because refrigerators were getting so efficient so rapidly, you would change out your refrigerator this frequently, which you could say is ridiculous. But if you want to minimize energy, even taking into account the energy to make a fridge, this is what you would do. Greenhouse gases is here. Now cost, it's saying you change it out about 15 years, which is what some people do. But I think some of you probably have fridges in your basement or your garage that are 20 years old. That's not a good thing, because you could actually save money and energy if you retire something. When we did this study, it was 94, but you could probably go 2001 and retire and save money and energy. Okay? So when you look at the food system, I talked about the overeating. And we looked at all the consequences of the food system. So we're overeating. There's diet-related disease that's over $70-some billion. And I just, again, want to benchmark Michigan. So we're in the 30 to 35% range of obesity. Okay? So interestingly, Colorado, they're pretty fit. But this is a problem. This is a serious problem, particularly for youth. And I'm going to take it a little further. I want you guys to calculate your, what's called the body mass index. So you take your weight in kilograms and divide it by your height squared in meters. So you ready to do that? All right, I'm going to help you. Take your height, come across to your weight, and go up and get the number. Everybody see their height? You go across to your weight. Everybody have your number? You can't see the numbers? Okay. Well, those that can, if you're in this range, so I'm overweight. Okay, I'm bordering on even being obese. Anyway, if you want to look at it later, you can. But this is an issue. You know, there's a lot of wasted food, and we're overeating. That's the biggest opportunity. And then, if you want to look at carbon intensity, what you're eating is also important. So this is what's consumed. This is the edible food that's wasted. But meat, clearly, we probably already know this, really drives carbon emissions. So we're doing work on trying to look at diets that are nutritionally optimal, but that meet the requirements, but also are cost effective and also that reduce environmental impact. Okay? So, and if you look at food issues, there's all kinds of challenges. There's food deserts. There's communities like Flint and Detroit. They don't have a lot of good food available. The greatest leverage point is in consumption. It's not necessarily how we produce the food, but it's our consumption of food. And diet shifts there's real opportunities. And our policies, we actually, there was some discussion about actually adopting sustainability into policy for food. But then it was modified a bit, and actually the meat industry had some influence in that. But it's really important that we look at the nutritional value of the food and how to deliver that. So I'm going to stop there. I guess we're at 12:30. I want to end with to thank you. And this is a saying that actually one of the Peter Wege was the first chair of our advisory board of our center, and he came up with this go blue and think green. Okay, so thank you very much.
And I'd be happy
to stay for questions. You probably want to let people break.
Could you put the body mass in?
Okay. I'm happy to, okay.
Do your studies justify the use of ethanol in gasoline?
Ethanol in gasoline is a complicated one, but if you look at the carbon emissions and look at the energy use, it makes sense. So if you take a unit of energy to make gasoline, so crude oil, and look at the BTUs. So for 1 BTU that we put into the refinery, we get 0.8 units, BTUs of gasoline out. So there's some losses, conversion losses. If I take that 1 unit, the 1 BTU, and put it into making ethanol, I'm going to get 1.2 out in terms of fuel because I'm leveraging the energy of the sun, right? So it's an improvement, and also there's a reduction in terms of carbon emissions as well. Now, It gets pretty complicated when you look at, there's a lot of different effects that can go on in terms of indirect effects, land use effects. Maybe that's your question.
I was just, how much you, so we talk about the blue-green economy, right? Water and energy efficiency.
Right.
And so when you think about ethanol, I know a lot of folks who are thinking on the blue side are concerned about ethanol. Corn is a nitrogen hog, there's so much runoff.
Right.
And not
We got eutrophication problems,
yeah,
definitely.
So I don't know if that ever gets factored into some of your models.
Oh,
the impact on water.
Yeah, so definitely there's impacts on water quality, water quantity, but from an energy point of view, it does look pretty favorable. I think in terms of strategies, electrification really gives you a lot of opportunity, particularly if we shift to renewable energy. You're going to really see dramatic improvements. But you're exactly right. There's trade-offs with all of, when you look at these things. Yes?
I think you may have had it on one of your very complex charts, but if you take a look at the energy balance of, let's say, Michigan's electric generation fleet, coal,
Right.
gas, and then take an all-electric car using that energy versus an efficient gasoline car. In terms of CO2, where does that come off?
So it depends on the efficiency of the car, but it could be very comparable. Yeah. So that's why we really need to, if we want to go with electrification, you have to change the mix. So, take one more question.
Is unique in terms of this kind of analysis, or are there other universities trying to keep up with you?
Well, we're actually leaders at the University of Michigan in terms of sustainable systems. We were actually established by the EPA, the U.S. EPA. We got a grant to establish the National Pollution Prevention Center in 1991. And we proposed to our advisory board, that's made up of industry and government and academics, that in 1997 we proposed to change to the Center for Sustainable Systems because we felt like prevention isn't enough. You really want to look at sustainability. You want to look long term. So less is better is one approach, but if you really want to look at these problems, you need to look at the long term. And we were doing life cycle modeling, so we proposed the name change to the Center for Sustainable Systems. People thought we were crazy back in 1997. But now you have sustainable energy systems, you have sustainable mobility, you have sustainable water, food. So we were really early, and we have a curriculum with our graduate school. We have dual degree programs. We have a program on engineering sustainable systems where you get a master's in sustainable systems and a master's in mechanical engineering or chemical engineering. We have a dual degree program with the business school. So I am proud. We are really leaders in terms of sustainability analysis. But there are other programs, coming up around the country. But I think University of Michigan definitely is one of the leaders there. Yes?
Does your group have a recommendation for Michigan on what you think the percentage of renewable energy should be?
Well, my colleague just 2 doors down from me did this study on looking at what's sort of cost effective in terms of strategy. And that report and that analysis showed it would be a 28%, sort of RPS, correspond to a 28% RPS.
So do you know if the legislature has reviewed that report or is considering it?
I'm not sure where in terms of the Clean Power Plan, I'm sure that's being discussed.
I was just going to ask if you were asked to testify or your information.
No, but my
renewable energy in the current bill
Yeah.
is pathetic.
Yeah.
I have a
Right.
bill for renewable energy, and it's.
Well, my colleague would be, we'd be happy to help out. I know in the first RPS, I testified both to the Senate and the House, and it was interesting at that time the reaction of people weren't even on board with recognizing climate change. I think we've changed. We've made some progress since then, but we could be a resource. So.
I'll get your information.
Okay. Veronica, I think, and I can give you a card too, but we probably should stop now because you guys have other things to do, and I really appreciate all the good questions and the discussion we had. So thank you very much.
On behalf of the University of Michigan Wolverine Caucus, we want to present you, Dr. Keolian, with this Wolverine Caucus pen.
All right.
Which has a real Wolverine on it.
Awesome.
So-
Thank you very much. I
All blue.
appreciate it. All right. Thank you.
Yeah, thank you
I'll
again.
wear it proudly.
Yes.
That's cool.
Yeah, it's nice. And to all of you, thank you for joining us today. And if you would like these slides, because I know several of you wanted to review some of them, I know I do. So I will make those available to you. Just let me know as you're leaving today. And we would like you to join us again on Wednesday, February 23rd, when we'll be talking about 3D printing innovations and beyond, as we look at how 3D printing now helps in saving lives.
What date?
That's Wednesday, February 23rd. 23rd. I'm sorry, Tuesday, February 23rd, excuse me. Tuesday, February 23rd. And again, that's 3D printing innovations and beyond, optimizing our healthcare with the use of new technologies. So we hope you'll join us again then, and have a pleasant and safe afternoon.
Right.